Welcome to this explainer. I'm absolutely thrilled to have you here today because we're going to learn how to crack one of the most fascinating visual codes out there, the human inheritance map. If you've ever wondered how geneticists track diseases, forecast risks, and untangle really complex family histories, you are definitely in the right place. So grab your mental magnifying glass because today we are becoming genetic detectives. I mean, really think about this for a second. How do scientists track a single genetic trait across centuries? How does a seemingly simple chart of shapes and lines predict a family's genetic destiny? It almost sounds like magic, right? But it's pure, elegant science. By the end of this explainer, you'll be able to look at a complex grid of symbols and read it like a gripping family biography. Okay, let's dive into our roadmap for today. First, decoding the genetic map. Then, shapes, shades, and symbols. After that, reading between the lines, charting the modern family, and finally, navigating the generations. So, kicking things off with decoding the genetic map, the basics of pedigrees. Now, you might be looking at this and thinking, wait, isn't this literally just a family tree? Well, not quite. A pedigree is way more powerful than those standard family trees you might build on a genealogy website. Sure, it shows familiar relationships, but it layers in some absolutely crucial clinical and genetic info. By mapping this out, geneticists can figure out exactly how a specific trait is inherited. They can predict genotypes, they can estimate linkages among genes, and this is the crazy part, actually calculate the mathematical risk of a genetic condition showing up in future generations. So it's really a predictive tool, not just a historical one. To really ground this, let's talk about the actual people involved when one of these is drawn up. There are two key terms here. The consultant, that's the person sitting in the office right now, receiving the genetic counseling and giving the family history. They're usually pointed out with an arrow on the chart. But then there's the proband, marked with a P and an arrow. That is the very first affected individual in the family to actually catch a geneticist's attention. And they're often not the same person. Like you might be the consultant in the office today, but the proband, that could be your great-grandfather who originally had the genetic trait being studied. Moving right along to shapes, shades, and symbols, the alphabet of genetics. Okay, so every single person on a pedigree gets a distinct shape. It's basically a code. Squares represent individuals who identify as male, and circles are for individuals who identify as female. If a person's gender is unspecified, maybe unknown to the person making the chart, or non-binary, we use a diamond. Oh, and a triangle, that indicates a miscarriage, and you might even see the number of weeks of gestation written right underneath to give a precise clinical timeline. Now, science is always evolving, right? It's getting more precise, and pedigrees are no exception. The National Society of Genetic Counselors recommends some really specific acronyms under these shapes to reflect clinical reality accurately. For instance, if someone identifies as a gender different from what they were assigned at birth, you'll see AMAB for assigned male at birth, AFAB for assigned female at birth, or UAB for unassigned at birth. Plus, if a person's sex chromosome karyotype is known to be something other than standard XX or XY, that specific genetic info is explicitly written right there beneath the shape. It just ensures the inheritance tracking is perfectly clear and medically accurate. Now, what's really interesting here is how we use shading to uncover hidden genetic truths. The shading tells us who actually shows the physical trait versus who is secretly carrying it in their DNA. A completely shaded shape, that means the person exhibits the trait. Completely unshaded means they don't. But check out that last point. An unshaded shape with a solid dot right in the middle, or sometimes it's half-shaded, that means the person is a heterozygous carrier. Basically, they have the gene, but they might not physically show the trait, depending on how strongly the gene expresses itself. Honestly, this is where the real detective work happens. We also have to track mortality, because that adds vital historical context to the family tree. It's pretty straightforward. A simple diagonal strike through a shape means the person has passed away, and you'll often see their age at death written right underneath. If the death was an infant stillbirth, the letters SB are used, followed by the weeks of gestation. This is super helpful for geneticists trying to spot patterns of early mortality that could be tied to inherited conditions. All right, let's move to reading between the lines, mapping relationships. Think of the lines as the roads connecting this whole genetic map. A horizontal line between two shapes, that's a relationship line, like partners. The offspring from that partnership are connected by a vertical line of descent, dropping down. And if there are multiple kids, a horizontal sibship line connects them all. Now, here is a golden rule for pedigrees. Siblings are always, and I mean always, drawn from left to right in birth order. So oldest on the far left, cascading down to the youngest on the right.
Twins are fascinating, and they get a very specific notation, a branching line that looks like an upside-down V. But you've got to look closely at the difference here. Monozygotic, or identical twins, come from a single fertilization event, so they're genetically identical. Because of that, they get a little horizontal line connecting the branches of the V. Dizygotic, or fraternal twins, on the other hand, come from two completely separate fertilization events. Genetically, they're no more similar than standard siblings, so there is absolutely no connecting line between the branches. It's wild how one tiny little line completely changes the genetic meaning. Of course, life is complex, and pedigrees have to account for that. 2 slash marks through a relationship line just means the relationship ended, like a divorce. We also need to be really clear about biological versus non-biological ties. Adopted individuals are put in brackets and connected with a dashed line. That clarifies that heritable genetic traits aren't being passed down that route. And finally, a double horizontal line means a consanguineous relationship, which basically means the partners are biologically related to each other. That is a massive red flag for geneticists to note because consanguinity dramatically increases the risk of the offspring being homozygous for a recessive condition. That means they could inherit the exact same hidden, potentially harmful trait from both sides. Up next, charting the modern family, assisted reproduction. As science, medicine, and family structures have evolved, the pedigree code has become brilliantly complex to keep up with it all. And this brilliantly illustrates how geneticists have to specifically track the origin of the sperm, the egg, and the gestational carrier. Like, look at pregnancy A. The sperm is from a donor, but the egg and gestational carrier are the female partner. In pregnancy C, the male partner provides the sperm, but a donor provides the egg and acts as the carrier. The solid lines on the chart will actually dynamically shift to connect only the biological contributors for each unique scenario. To keep these complex situations straight, we throw a few extra letters inside the shapes. A P denotes a current fetus, a D stands for a sperm or egg donor, and an S denotes a surrogate. Now here's a really fascinating biological detail for you. Even if a gestational carrier or surrogate doesn't contribute a single drop of DNA to the fetus, they are still connected with a solid biological line on the pedigree. Why? Because the uterine environment is still biological. Things like maternal preeclampsia or exposure to teratogens, substances that can disrupt fetal development, those are critical pieces of medical info that absolutely must be tracked. Let's actually look at a highly specific real-world scenario from the source material to see this in action. Imagine a family where the egg comes from a transgender man and the sperm comes from his partner, a cisgender man. But the pregnancy itself is carried by a surrogate, marked with an S. The pedigree will draw biological lines from the two men providing the gametes, and then another line to the surrogate carrying the child. It just shows exactly how precise and really how wonderfully inclusive these modern visual maps have become, making sure literally every medical variable is accounted for. And finally, navigating the generations, creating the master grid. When you start mapping out great-grandparents, cousins, donors, twins, these charts get absolutely massive. So how do scientists avoid just getting completely lost? Well, they use a master coordinate system. It's done in 3 pretty simple steps. Step 1, you label every generation vertically down the side, using Roman numerals. Generation I at the top, generation 2 below that, and so on. Step 2, everyone in that same horizontal plane gets numbered from left to right using standard Arabic numerals, 1, 2, 3. Step 3, combine them. This creates a totally unique identifier for every single person. So if a geneticist wants to point out the oldest daughter born to parents in the 2nd generation, they literally just say, look at individual I31. Instantly, everyone is looking at the exact same shape on a chart of hundreds. It's incredibly efficient. So we've decoded the shapes, traced the lines, and navigated the grid. You are officially equipped with the tools of a genetic detective. But before we wrap up, I want to leave you with this thought to ponder. What would your unique genetic map look like if we drew it out today? Who would be the proband? Where are those hidden carriers? The entire story of your past and maybe even a glimpse into your future is all right there, just waiting to be drawn. Thanks so much for joining me on this explainer, and keep exploring.